Alright, so hyperbolic tangent and hyperbolic tangent inverse are given by the green and the pink curves. Once again, hyperbolic tangent inverse of x is y, if and only if hyperbolic tangent of y is x. The domain of hyperbolic tangent inverse will be the range of hyperbolic tangent, and the range of hyperbolic tangent is -1 to 1, excluding -1 and 1. What's the range of hyperbolic tangent inverse? With -infinity to +infinity, because that's the domain of hyperbolic tangent of x. Anytime I have two inverses, the composition of the two in any order will give you the identity function. So hyperbolic tangent evaluated at hyperbolic tangent inverse of x is x, and also hyperbolic tangent inverse of hyperbolic tangent of x is x. In the first equation, x is in the domain of hyperbolic tangent inverse. In the second equation, x is in the domain of hyperbolic tangent of x. Now, what I want to do today is the following. Let me not show you inverse formulas yet. Let me go back to the definition of hyperbolic sine. So, like I said, we are going to concentrate on hyperbolic sine, hyperbolic cosine, and hyperbolic tangent. The other ones we are not going to discuss, but you can imagine there will be a very similar discussion, and you can find these formulas almost anywhere now. So if you ever see hyperbolic cosecant or something else being used in any class or anywhere, you know where to look for. Yeah.
Did you say when you have the inverse hyperbolic tangent, then you have the hyperbolic tangent inside the whole
I'm going to go back there. Yeah. So what I want to mention though is that I have these three functions. Notice that these functions are really defined in terms of the exponential, right? And we define the inverse of each one of them, right? The inverse of each one of them. Now the question is, because these functions are in terms of the exponential, would you suspect that the inverse of these functions will be in terms of natural log? Because natural log is the inverse of the exponential. So because these functions are defined by the exponential, you would suspect that the inverses of this function will be given by the natural log. And that's the case. And if I go down, I was going to show you these formulas here, that I can express hyperbolic sine inverse in terms of log of x plus root of x squared plus 1. Hyperbolic cosine inverse will be log of x plus root of x squared minus 1. And the third one is hyperbolic tangent inverse of x is half ln of 1 plus x over 1 minus x, where x is between, of course, these are the domains of the respective functions, right? Remember, the domain of hyperbolic sine inverse is all reals. The domain of hyperbolic cosine inverse, though, is 1 to infinity, because the range of hyperbolic cosine was 1 to infinity. And the domain of hyperbolic tangent inverse is this one, because that's the range of hyperbolic tangent. Now let me show you the graph of hyperbolic tangent again. See, hyperbolic tangent, the range is from -1 to +1. But the domain is all real numbers. The domain of hyperbolic tangent is all real numbers, but the range is from -1 to 1. It doesn't include -1 and 1. So if you look at the hyperbolic tangent inverse, then the hyperbolic tangent inverse will have domain between -1 and 1, and its range will be from -infinity to +infinity. The opposite of hyperbolic tangent. Is that okay? So now the question is, how do you derive these three explicit formulas for the inverse hyperbolic function. So I am going to derive for you number 3. Why did I choose number 3? Just because I had to make a choice, but another reason is number 1 is derived in your text, and number 2 is very similar to number 1 in the derivation of it. So number 3 is not done in the text. It's a little bit different from the first 2. So I thought I'll do number 3. If you want to see number 1, you can look it up from the text. But they are all done in a very similar way. So I'm going to derive for you number 3, and let's see how we could do it. So I am going to let y to be a hyperbolic tangent inverse of x, and I want to express it explicitly in terms of the log function. So how would I be able to do it? Well, if y is hyperbolic tangent inverse of x, what can you say about x? Well, x would be hyperbolic tangent of y, right? They are inverses, so they do the opposite of each other, meaning that hyperbolic tangent inverse of x is y if and only if hyperbolic tangent of y is back to x, right? So I have hyperbolic tangent of y is x. Now what is hyperbolic tangent of y? Well, hyperbolic tangent of y in terms of the exponential, it is what? E to the y minus e to the minus y divided by e to the y plus e to the minus y. I defined that last time, right? So let's go back to remember hyperbolic tangent of x was this function, right? E to the x minus e to the minus x over that. So I'm just using that definition. So I get this. Now what is my goal? My goal is to find y, right? My goal is to find y. So from this equation, how would I find y? How would you solve for y? How would you solve for y from this equation? One thing that I'm going to do first is the following. I am, let's say, I am going to the left hand side. On the left hand side, I am going to do the following. I have e to the y minus e to the minus y over e to the y plus e to the minus y. I am going to multiply and divide by e to the y, okay? E to the y. And now if I multiply out, what do I get? If I multiply out the numerators, I'm going to get e to the 2y minus 1 over e to the 2y plus 1, and this is equal to what? This is equal to x. So on the left hand side, I basically simplified the left hand side, right? I got rid of the negative powers. Now I'm going to think of x as x over 1 and cross multiply. So if I cross multiply, I am going to get what am I getting? Okay, I'm getting e to the 2y minus 1, and I'm going to get x e to the 2y plus x. Am I correct? Cross multiplication. And then I need to, I want to solve for y, right? So let's get the y terms together. So let's get e to the 2y minus x e to the 2y. And then on the right hand side I have x, and the negative one that I have on the left, we are just going to send it to the right. So I am going to get 1 plus x. Is that okay? Alright, on the left hand side, can I factor out something? I can factor out e to the 2y, and if I do that I get 1 minus x. And finally I could say, hey, e to the 2y is 1 plus x over 1 minus x. I need to find what? Okay, how do I find y from here? Yeah, you apply log, and if you apply log on the left hand side, you are going to get 2y, and if you apply log on the right hand side, you're going to get 1 plus x over 1 minus x, and finally y would be what? Let me just say y is half of that, as I am out of space here. So that's exactly the formula that I wrote down for you in number 3, and I gave you the formula in my handout as well. Is everybody okay? This is how you can derive. This is pretty simple. It's just a matter of some algebra. Alright, now once I have this 3 explicit formulas for the for this inverse hyperbolic functions, the next thing I want to do is I want to look at the derivatives of these inverse hyperbolic functions, and here are the derivative formulas. For the inverse sine, the derivative is 1 over root of 1 plus x squared. The second one is 1 over root of x squared minus 1, and the third one is 1 over 1 minus x squared. How are these different from the trig functions? For inverse sine, what do I have here? For inverse sine, what's the derivative? This would be a negative sign, right? For inverse sine. For inverse cosine is really quite different, because inverse cosine would also be 1 minus x squared here, and there is a negative 1 here. But here I have root of x squared minus 1. And for inverse tangent, we had 1 plus here. It is 1 minus 1. Very similar formulas, but a little bit different. And remembering which one is plus and which one is minus sometimes could be a little bit problematic.
You know all 6 functions from the regular. So inverse secant, inverse cosecant, we need their derivative. Not the hyperbolic.
For the when I sent you the syllabus for the exam too, right? I said specifically it is going to be on the handout on inverse sine, inverse tangent, and inverse secant. So you don't have to worry about the other ones. Okay, so all right. So maybe we can derive one of them. In your homework for this section, there is one problem where it is asking you to derive the derivative formula for the inverse hyperbolic cosine, or some of you might have inverse hyperbolic sine. The way it is done there in your homework is different from the way that I'm going to derive the derivative. And you can see how I'm going to derive it differently. I already have some explicit formulas for this inverse functions, right? So do we know how to find the derivative of all these 3? Yeah, by chain rule, right? We know how to find them. And I'm just going to do that. But in your homework, they derive number 1 in a little bit, not number 1 here, the derivative formula number 1, in a little bit differently. The method that is used in your homework is similar to the method that we employed for finding the derivative of sine inverse, cosine inverse, tangent inverse. So since I have done that before, I'm not going to do that here. So let me just derive that for you. It's just going to take a minute. So we are taking the derivative of, I'm just going to do number 3 just because 1 and 2 are basically in your homework. So what is the derivative of inverse hyperbolic tangent? Well, we have an explicit formula for that, which is ln of 1 plus x over 1 minus x. Actually, we have a half here, right? Okay, and so now I'm going to take the derivative of that, which we should know how to do. So basically what I'm going to do, I'm going to take the half outside of the derivative. because that is a constant factor and it is valid. It is valid to take it out. Right? Now, I can take the derivative by using the chain rule as it is, but before I use the chain rule, what I'm going to do, in fact, is I'm going to rewrite this by using the log rules. So before I take the derivative, I am going to rewrite my expression as ln of 1 plus x minus ln of 1 minus x. Okay, and once I have this, now I would say that I'm going to go ahead and take the derivative. What's the derivative of ln of 1 plus x? 1 over 1 plus x. What's the derivative of ln of 1 minus x? 1 over 1 minus x, and I have to multiply by a negative 1, isn't it? Right? Why negative 1? Because derivative of 1 minus x is negative 1. And then you can see that it's basically plus, right? So I'm just going to do it here. I'm going to make it a plus and get rid of that negative 1. And now we're just going to do simple algebra. Okay, is there anyone who doesn't know how to add these two fractions? Combine them into one fraction. How would you do it? Take the common denominator, right? What's the common denominator? What's the common denominator? Yeah, 1 plus x times 1 minus x, or 1 minus x squared. And then what do? I know that in the numerator I'll be getting two terms, right? So I'm going to put a plus. Two terms. What's the first term? How do you obtain the first term? The first term is the first numerator multiplied by what? Yeah, you divide the common denominator by the first denominator, whatever that is. That is 1 minus x. And here, this is the second numerator 1 multiplied by what? 1 plus x. Is everybody okay? Alright, so this is what? Half. I'm just going to blindly say that I have a 2 in the numerator, because that better be the case. Otherwise I gave you a wrong formula. But you can simplify that. You can see that if you simplify that, you're going to end up with 2. And that's exactly the derivative. Everybody's okay with that. And you can take the derivative of the sine inverse, hyperbolic sine inverse, and hyperbolic cosine inverse in a very similar way. All right, so this is it. So this is the end of hyperbolic functions. Oh, I want to mention one thing, just to show you that these functions. How many of you have seen these functions before, like in a science class or engineering class? Maybe you guys it's too early for you to maybe see any of these functions anywhere else, but they do come up in many applications. For example, if you look at the velocity, so you're trying to model the velocity of a water wave. Let's say the depth of water is d, the wavelength is l. Then the velocity can be modeled by using this formula where the hyperbolic tangent function appears. Okay. And here, of course, g is acceleration due to gravity, and all the other terms are defined. Okay. Now, again, just to show you that these functions are studied not because of mathematics, because there are lots of applications that involves these functions. All right, so this is the end of hyperbolic functions. Any questions at all? Is there any part in my discussion that confused you? Maybe I should go over again. I did go pretty fast yesterday over the hyperbolic functions, but the video is up. If you want to take a second look at it, you can, or you can just ask me questions if you have any. All right, so let me say that we are done with this then, if you don't have any questions. And then maybe I can try to see if you have any other questions. I'm going to go ahead and